So let's take a problem based on kinematics. Based on kinematics. So here I am writing the problem. Rope to which a weight is attached. A weight is attached. Passes around a pulley of 50 centimeter diameter. The angular acceleration of the pulley, angular acceleration of the pulley is 18 radian per second square. If the pulley is initially at rest, find number 1 the time required for the weight to attain a velocity of 15 meter per second. Part 2 the number of revolutions through which the pulley rotates during that period. Number 3 total acceleration of a point on the ring of the pulley 0.5 seconds after it was at rest. So this is the given problem. Let's solve this problem. That is for part 1. We are interested in time required for the weight to attain velocity of 15 meter per second. Velocity is given, that is 15 meter per second. But we are dealing in rotational motion, so we have to find corresponding angular velocity. We know omega is v by r and the diameter is given, that is 50 centimeter. So r will be 25 centimeter. So it will be 25 by 100. Omega will be v, we know 15, and this one is r is 25 by 100. Omega will be 60 radian per second. So that is the angular velocity corresponding to 50 meters per second. And now we can use the for equations for circular motion. I am using omega equals to omega 0 plus alpha t, and here in this problem alpha is given, that is 18 radian per second square. If I put all these things in that equation, omega we know 60 omega naught, because it is starting from rest, so 0 plus 18 into t, so t will be 60 by 18, it will be 3.33 seconds. So the answer of the part 1, that is the time required for the wave to attain a velocity of 15 meter per second, is 3.3. Second part, we have to find out number of revolutions through which the pulley rotates during that period. So we can use the other equation, that is theta is to omega naught t plus 1 by 2 alpha t square. We know the initial angular velocity, that is 0. We have already calculated the time, that is 3.33 seconds plus 1 by 2. We know the alpha, that is 18, and again time is 3.33. So the theta value will come 100 radian. But we are interested in number of revolution. Number of revolution can get theta by 2 pi 100 and 2 pi will be 15.92 revolution. So the correct answer for the second part is number of revolution will be 15.92. Now for the third part, we have to find out total acceleration. First find tangential acceleration. So tangential acceleration is nothing but AT is R alpha. So we know the value of R is 25 into alpha is 18. So it will come 450 centimeter per second. So the normal acceleration now, normal acceleration is nothing but am equals to r omega square. But we have to find out after 0.5 seconds numbers. So after 0.5 seconds we have to find out what is the value of omega. So omega equals to omega 0 plus alpha t. So omega initially is 0 plus alpha we know it is 18 here, and t is 0.5, so omega will be 9 radian per second. So the normal acceleration r omega square we can write, it is 25 into 9 square, so it will come 2025 centimeter per square second. So now we are having tangential acceleration 450, we are having the normal acceleration 2025. So total acceleration we can easily find out. Total acceleration is nothing but a equals to at square plus an square. So total acceleration at means 450 square plus an is 2025 square. And if we solve this thing, we will get the value of a is nothing but 207414 centimeter per square. This one is the desired acceleration of a point on the rim of a pulley 0.5 second after it passes at rest. Now we will discuss about the kinetics of rectilinear motion. Kinetics of rectilinear motion. So now we are discussing with the kinetics, means here we are interested in forces and couples which are responsible for motion. So now in kinetics of rectilinear motion, we have to consider the forces and couples which are responsible for motion. So analyzing the problems based on the kinetics of rectilinear motion, the D'Alembert's principle is very important. D'Alembert's principle. So D'Alembert principle is very important in analyzing the problems based on kinetics of rectilinear motion. As we already discussed, kinematics and kinetics, the branch of dynamics. It means the dynamics deals with the bodies which are in motion. So according to the D'Alembert principle, if the body is in motion and if we want the equilibrium of these bodies, means if we want the dynamic equilibrium of that body, then we have to apply the inertia force in opposite direction of the motion, then we can say that the body is in dynamic equilibrium. So I am writing the principle of D'Alembert. According to the D'Alembert, for dynamic equilibrium, dynamic equilibrium, if we apply an inertia force in direction opposite to direction of motion, then body will be in dynamic equilibrium under the external forces as well as inertia forces. So I would like to again repeat the D'Alembert principle. So for D'Alembert principle, uh, it is talking about dynamic equilibrium. If we want the body will be in dynamic equilibrium, then we have to apply an inertia force which will be in direction opposite to the direction of motion. Then the body will be in dynamic equilibrium. Or in other words, if the body is in dynamic equilibrium, it means it is under the action of external force as well as the inertia force. So let's talk about a simple body, simple blocks there, and we are applying a force F. And now, if we want this system is in dynamic equilibrium, then we have to apply an inertia force which will be in the opposite to the direction of motion, and we know the inertia force value will be mass into acceleration. So I can write F minus ma equals to 0. So with the help of D'Alembert principle, we can write this equation F minus ma equals to 0. It means the net force is 0, so we can say that it is in dynamic equilibrium. So the D'Alembert principle is very useful in solving the problems based on kinetics. Now let's take a simple problem. Let's take a simple problem based on D'Alembert principle. So I am just writing the problem. An elevator weight 25 kilonewton is moving vertically downward with a constant acceleration. Write the equation for the elevator cable tension. I am just repeating the problem. An elevator which weight is 25 kilonewton is moving vertically downward with constant acceleration, and we have to write the equation for the elevator cable tension. So let's solve this problem. First of all, we will draw the diagram which will show all the forces. This is the elevator. mg is the weight of the elevator which is always acting downward direction. This one is the T tension in the elevator cable, and now it is going in downward direction. So this one is the motion, and now we have to apply the D'Alembert principle. But for applying the D'Alembert principle, we have to introduce the inertia force which will act in which will act in the direction opposite to the direction of motion. So the direction of motion of the elevator is in downward direction. So the inertia force will act opposite to that. It will act in upward direction. So the inertia force will act in upward direction. And the value of inertia force we know that is mass into acceleration. Now this elevator is in dynamic equilibrium under the action of T, mg and ma. So now it is in equilibrium, so we can apply the conditions of equilibrium. That is algebraic summation of all vertical forces should be 0. So in vertically upward direction we are having T in upward. So according to our sign convention, vertically upward is positive, vertically downward is negative. So this one is positive. Vertically up, the inertia force Ma is also in upward, Ma, and Mg is in downward. So, so I can write T equals to Mg minus Ma. So now T equals to, if we take Mg out, it will be 1 minus Ma by Mg. So we can get T equals to Mg 1 minus A by G. So this one is the desired equation for the elevator cable potential. So by simply applying the D'Alembert principle, we can convert the problem into dynamic equilibrium, and then we can apply the conditions of equilibrium for solving the values of unknown. A very important problem based on kinetics. Problem based on kinetics. So here I am drawing the diagram for understanding of the problem. A drum is given and the radius of this drum is 37.5 centimeter and the weight of this drum is 1.8 kilonewton and the radius of gyration for this drum is given, that is 30 centimeter, and a string is wound on this drum and the other end of the string is connected to a weight of 1 kilonewton here. And now in this problem we are interested in acceleration of weight, angular acceleration of drum, angular acceleration of drum, and tension in rope string. So here in this problem we are interested in acceleration of weight, angular acceleration of drum, or tension of string. So we can apply the D'Alembert principle here for solving this problem. So let's draw the free body diagram of weight 1 kilonewton. So we will make this body is in dynamic equilibrium and apply the condition of equilibrium. So this 1 kilonewton weight is acting in the downward direction, it is nothing but 1000 newton, and here tension T which is acting in upward direction. And now according to the D'Alembert principle, if we apply the inertia force in opposite direction of the motion, then it will be in dynamic equilibrium. So for this block, motion will be in downward direction. This one is the direction of motion. So inertia force we can apply opposite to that, in upward direction, and the magnitude is nothing but mass into A. So now we can apply the conditions of equilibrium, that is algebraic summation of all vertical forces should be 0. According to our sign convention, vertically upward is positive, vertical triangle is negative. So we are having plus T plus MA minus 1000 equals to 0. So we can write this thing T in place of M. I can write 1000 by G, because if we divide weight by G, we will get mass. A minus 1000 equals to 0. So this is the expression we got from our equation, that is algebraic summation of all vertical forces we see. So let's say this one is the equation number 1, and now we will draw the free body diagram of the drum. So before drawing the free body diagram of the drum, we have to visualize the motion of the drum. Drum will have the rotatory motion. Then we have to talk about inertia of the drum, and how we can calculate the inertia of the drum first. So first calculate the moment of inertia of drum. Moment of inertia drum. So we know the moment of inertia we can calculate by mk square here. M is the mass and k is the radius of gyration. So here mass is given, so 1800. This one is the weight. If we divide it by 9.81, we will get the mass. Radius of gyration is given 30 centimeter to 0.3 meter. And if we simplify it, we will get 16.5 kg meter square. It is the moment of inertia drum. So now let's draw the free body diagram of drum. Free body diagram of drum. So here, free body diagram of drum, we are having the rope here. So we have to see the tension here, T, and this distance we know is 37.5 centimeter. So now it is in rotatory motion. So first of all, we have to find the torque of that. So torque, suppose tau, torque acting on it, that is tau, will be T into 37.5 by, okay, so will be 0.375 T. So the tau means torque which is acting on the drum will be 0.375 T. So now only the torque is acting on a drum. Now according to the D'Alembert principle, if the body is in dynamic equilibrium, then there will be an external force as well as the inertia force. So here I am just showing the torque. So if we apply the inertia torque here in the direction opposite to the motion, then it will be in dynamic equilibrium. So for dynamic equilibrium, we are interested in inertia torque also. Inertia torque. So inertia torque, like for inertia, we are having mass into acceleration. So similarly, in rotational motion, in place of mass, we are having I, in place of A, we are having O. So we are having I. So I, we are having 16.5. So now we can apply the conditions of the equilibrium, that is algebraic summation of moments of all the force above O should be 0, or moment should be 0 at the point O. So from that I can write 0.375 T minus 16.5 alpha is to 0, because here I am considering the external torque and here I am considering the inertial torque. Similarly, like F minus ma equals to 0, so here I am having T minus inertial torque equals to 0. So I am having the equation number 2. Now we know linear acceleration equals to r into alpha. So r we are having 0.375 alpha. So a we know that is 0.375 alpha. Put value of a in terms of alpha in equation 1. We will get t plus 1000 a by g minus 1000 equals to 0. It is equation number 1. So we can again rewrite t equals to 1000 minus 1000 a into g, and if we put the value of a in terms of alpha here, that is 1000 minus 1000 into 0.375 alpha, and if we put the value of g, that is 9.81, so we will get t equals to 1000 minus 38.226 alpha. So now we are having the expression t of t in terms of alpha. Now put this t, the expression of t in equation 2. So equation 2 is 0.375t minus 16.5 alpha equals to 0. If we put the value of t in terms of alpha here, we will get 0.375 to 1000 minus 38.226 alpha minus 16.5 alpha equals to 0. If we further simplify it, we will get 375 minus 14.335 alpha minus 16.5 alpha equals to 0, and by this way we get alpha equals to 12.16 radian per second square. And we know a is nothing but 0.375 alpha, so we can get the value of a, nothing but a linear acceleration, 0.375 into 12.16, so we will get 4.56 meter per second. Now put the value of alpha in the expression of t, that is t equals to 1000 minus 38.226 alpha. So I'm putting the value of alpha here, that is 1000 minus 38.226. Value of alpha we know that is 12.16. So we can easily get the value of t. So 535.2 meter. So now the acceleration of the weight we know that is 4.56 meter per second square. Angular acceleration of drum, that is 12.16 radian per second square. The tension in the rope string is 535.2 meter. So by this way, means by the application of D'Alembert principle combined with free body diagram and applying the equation of equilibrium, we can easily find out the unknown value.